So now that we've seen some exponential functions of growth and decay, we want to kind of just start seeing how we can use these, what are some applications, what are some functions we can use with these. So obviously if we say exponential growth, it's something that's going up, and something that is decaying is going down. So exponential growth typically looks something like this. We'll say it's some kind of function with respect to t, where we have a, which is some starting amount, what you'd start with, 1 plus r. R would, of course, be your rate, like how much it's growing, to the power t. So a, as you can see, and this is all right here for you, a is the starting amount, initial amount, r is the growth or decay rate, and t is the length of time. So if it's decaying, the only difference is going to be instead of adding that rate, we're going to subtract it, because instead of going up, it is going to go down. So it's 1 minus r to the t. So you have exponential growth and exponential decay. So our goal today is just to set up some of these equations and do some pretty basic things with them. So for example, this first thing says Brooke started her career with an annual salary of $32,000. Sounds like an initial value. Each year, her salary increased by 2.5%. Write an exponential growth function to find her salary when she retires after 30 years. So it is a growth function, so we know it's going to be f of t equals a 1 plus r to the t. So what we do is we put the starting amount first, so that'll be $32,000. Parenthesis, now the rate is 2.5. Now the big thing when you put a percentage into an equation, we have to make sure that's a decimal, so 1.025 to the t. Because we don't know t, and then we don't know the functional value at t. Now, if you want, you could certainly add those two things together. You could add the 1 plus 2.5% and get 1.025 to the t. So that is our function. So for now, we're going to have values of t. Eventually, we can figure out how long it will take to do this, but that'll take a little more algebra. But for now, we want to know how long until how much money is she going to make when she retires after 30 years. So t is 30. So I'll just figure out what is f of 30. So f of 30 is going to be 32,000, pardon me, 1.025 to the 30th power. And you could just put this in any calculator you'd like, and I'm getting $67,122.16. I would highly encourage you to pause this video for these problems, put it in your calculator, make sure you're getting the same thing I am, because that is one of the key things, making sure you can put this in your calculator and get the correct value. So we look at this next one. It says in a 1995 magazine, it had 14,000 subscribers. The number has increased by 40% each year. How many subscribers in 2016? So again, we're growing. So f of t, we're going to start with 14,000. And our growth rate in this type is 40%. So that's 1 plus 0.4 to the t. So quite a quick growth rate. And of course, you could certainly put those together. That's no problem. You can make this 14,000, 1.4 to the t. Now we have to kind of figure out what do I plug in for t? Now it says that we start in 95, and we want to know in 2016. So if I want to know how many years between 2016 and 1995, that is 21 years. So we wouldn't plug in 2016, we would plug in t of 21. So to find this value, we say, what is f of 21? Well, that's 14,000, 1.4 to the 21. Well, it's not dollars in this case, it's subscribers. So this is giving me 16,398,978. So you go from 14,000 subscribers to 16 million. In 21 years. Now, of course, this is a 40% growth rate, so this is an extremely aggressive growth rate. Most things don't grow that fast. All right, let's look at another one. Kate drank an energy beverage with 150 milligrams of caffeine each hour the amount of caffeine decreased in her system. So that's good. This is a decay problem by about 12%. Write the decay function and figure out how much caffeine in 8 hours. So very typical when you take caffeine or any kind of medicine, the amount decays in your system after a certain time. So decay, remember, is f of t equals a 1 minus r to the t. So our initial amount, there's 150 milligrams to start with, and then it's 1 minus 12, so 1 minus 0.12 to the t. So my exponential equation is simply going to be 150 to the 0.88 t. And then I'll use this to figure a value out. I want to know how much is in there after 8 hours, so that's f of 8. So 150 to the 0.88 to the 8. And so that's going to give me 53.95 milligrams. And again, go ahead and check that. Make sure you're getting the same thing that I'm getting. All right, now let's look at the last one. The last one has a little trick to it in the time, as you'll see. It says the half-life of mercury is 3 days. Okay, so 3 days is its half-life. Write and use an exponential decay function to find the amount of mercury left from a 50-gram sample after 20 days. Okay, so this is a little different. We have a half-life. Now, a half-life basically is how long it takes for something to reduce in half. So it goes from a certain amount to half of that in every 3 days. So the way we do this is we would say f of t. So we start with 50 grams. And our decay rate is, doesn't really tell us the decay rate, but it's saying half-life. Now half-life is basically it reduces by 50%. So let's say 1 minus 50%. Half-life is always 50% because you're basically cutting in half. Now the weird thing about half-life is because our half-life is 3 days, we took it to the power of t over 3. T over 3. So that's kind of a weird one. So this is going to simplify to 50, 0.5 to the t over 3. That's going to be our growth. So if I want to figure out how long after 20 days, I'll just plug it in. So f of 20, maybe, is 50 to the 0.5 to the 20 over 3. So that is going to give me 0.49 grams. So this obviously reduces pretty quickly because it's cutting in half every 3 days. Every 3 days it's cutting in half. 10 to 5 to 2.5 to 1.25. Keeps cutting in half every time. Now another kind of growth function we will see is what's called a continuous growth or decay function. So instead of going up or down in certain increments per certain days, it's always going up or it's always going down. Kind of like things work in nature. It's always increasing, always decreasing. So that formula is a little different. So the big thing is you have to have, the word continuous or constantly, things like that. So these functions look like this. We're going to say A, which is the amount, equals P e to the RT. Now this is the amount. P is going to be the initial. We don't use A because we kind of use A for the amount. R is the rate, obviously. T is the time. Now we have E. Now E, if you remember, E is some kind of magic mathematical constant. It's about 2.71828, blah, blah, blah. It's a number like pi. It's this magic number that happens in nature, and it's just a button that you can see on a calculator or anything like that. So it's not really something you'll plug in for. It is a constant. So you're always looking for things where it says continuously to do problems like that. And if your rate is positive, it's going to go up, and if it's negative, it's going to go down. That's how we typically deal with continuous things. So if we look at this problem, it says a garbage dumpster started with 4 pounds of garbage. And it increased continuously. So whenever I see continuously, I know I'm going to use this formula versus the general growth or decay. And then continuously 35% every day from this point forward. Find the amount of garbage in 2 weeks. Okay? So I'm going to start with 4 pounds of garbage. E is some number. I don't change that. My rate is 0.35, and I don't know the time. So this is my generic equation. And then obviously I'll plug in my time. But I always want to kind of start by figuring out what the equation is. And then I know my time is 2 weeks, which is 14 days, which I can plug in. But I always like to make the equation first because you don't know. You might have to do a couple different things with the equation. So if I put this in, again, E, on Desmos, you can literally just type E if you're using a handheld calculator. It's literally second division or second multiplication. There's usually a button that says E. And that's going to turn out to be 537.16 pounds. So even though it grows continuously, it's not like it goes infinitely fast, infinitely big. It goes fast, but not really that much bigger than general growth and decay. So let's look at number 6. It says a population of a town is declining at a continuous rate of 1.5. So it's going down. If the current population is 16,000 people, find the population in 8 years. So again, we have this continuous idea, so we're going to use the A equals. So P is what we start with, which is 16,000 E. Now again, it's going down at 1.5. So the way we deal with this is we say negative 0.15. And again, it is 0.15 because it's 1.5% and then T. So there is my decay equation. And then for our problem, we're going to plug in 8, because we don't know how long it is in 8 years. And it's 1.5 every 8 years. So 16,000 E to the negative 0.015 to the 8. Now again, sometimes you got to make sure, like when you're doing this, when you have multiple things, sometimes you got to put an extra set of parentheses. I'd again highly encourage you to try this. So I'm getting 14,190 people in the population. So in 8 years, it's only gone down from 16,000 to 14,000. And so not a very fast decay, generally because you only have a 1.5% decay rate. So it's not going down all that fast. The last kind of function we'll look at is one we're really not going to create, but we can certainly see the graph of and kind of use, and it's called a logistic function. So logistic functions are kind of like exponentials where they flatten out and then they increase pretty quickly, but instead of going up forever, they level off again. Lots of natural phenomena we'll see will do that. A lot of diseases do this. They will be very, very slow to start off. You'll get a lot of people get infected, and then it will level off again. So most of these will have to kind of have the equation given to us. So they're pretty odd. C over 1 plus A to the E to the negative RX. So pretty bizarre. The big idea is you're essentially going to find out how long these things behave after a certain amount of time. Now, this is something I definitely want you to try. Put in your calculator, practice this, because these are not easy. So it says a disease begins to spread in a town of 20,000 people. After T days, the number of people who have been infected by the disease is modeled by the function below. Use the function to figure out the number of people infected after 10 days. So there's really nothing to this. We're just trying to find f of 10, but plugging it in can be somewhat challenging. So 20,000 over 1 plus 1150 E to the negative 0.95 times 10. You might want an extra set of parentheses here, especially if you're using Desmos. So go ahead, pause the video, try to put this in, see what you get, what I get. So I got 18,415 people. So it's gone down. It's gone down from 20,000 to 18,400. So it's going down. So we're getting less people with this disease. Okay. All right, last one. A population in millions of a country from 1850 to 2000 is modeled by this equation. Using the function, find the number of people in 1920. Well, 1920, if we start in 1850, and then t is going to obviously be 70 because there's 70 years between those. So that's what I'm going to plug in for this population. Now, obviously, we would assume that this is going to give us a pretty big population as population grows. So 135 over 1 plus 58 e to the negative 0.025 to the t. So, again, try this, put it in your calculator, see if you get what I get. So I'm getting 12.19, and since our unit is in millions, this is going to be million people. So these are a couple kinds of exponential models you can see. So go ahead and work on the assignment and let me know if you have any questions.